So we've talked about what solids, liquids, and gases are. So we're going to kind of do a little bit of review here. This table from your textbook compares the three states of water: solid, liquid, and gas. We call solid water ice, and we call water in the gas phase steam. So here are the temperatures at which these would exist. The densities. We see that the density of ice and water, those are similar. They're about 1 gram per milliliter. The density of steam is much, much less. If we look at molar volume, the volume of 1 mole, so the volume of 1 mole of water is 18 milliliters, solid water 19.6, similar, but the volume of 1 mole of water in the gas state is 30.5 liters. So there's a lot of empty space. When we look at the illustrations here, in the gas state there's a lot of empty space between the molecules. In liquid water and solid water, the molecules are touchingly close. Intermolecular forces are effective at very short distances. So here we have intermolecular forces playing a big part in the liquid and the solid forms. In the gas state, the particles are very far apart, and this is not even to scale. There's actually more space than is illustrated here. And so the effects of the intermolecular forces are very, very small.
Why is water more dense than ice?
Why is water more dense than ice? That's an excellent question. We're going to talk about that later, but I'll tell you right now. When ice forms, the molecules line up in a particular crystalline pattern, which actually creates a little more space between the molecules than when they're just randomly arranged as a liquid. And so it becomes slightly less dense. That's a very unusual feature of water. Most solids are more dense than the liquid. So, if you take pretty much anything else and you have the solid and the liquid together, the solid will sink to the bottom of the liquid. Whereas with water, the solid floats to the surface. And that has a huge impact on all sorts of things in life. So the biggest difference between solids and liquids is the freedom of movement of the particles. Their densities are similar, the molecules are touchingly close, but the big difference is that in a liquid, the particles can swim around, they can move relative to each other. I think of a crowd of people just milling about, right? Just moving around. Whereas a solid, the particles are fixed. It's like you're standing in lines or something, or sitting in chairs on an airplane maybe. And you're not moving relative to each other, and yet each individual person is moving, they're breathing, right? They're fidgeting or whatever. So solid particles will vibrate, but they're locked in position. So we have, again, the densities of liquids and solids are similar. The difference is that the shape is indefinite for a liquid, and it's definite for a solid. So we've got these three things: density, shape, volume, and gas, liquid, and solid. And two of these will have something in common, and then the third will be different. And so you need to understand these relationships. Okay? Question?
What's thermal energy again?
Thermal energy is the kinetic energy of the vibrations and the movements of the particle. So it's related to temperature. So the warmer the temperature, the more the particles are moving. And so the way I think of, say, ice melting, so you've got ice and you've got, people sitting in chairs in a very organized way. And as the temperature rises, the people get really agitated. And they're like just jiggling and wiggling, and finally they just can't stand it anymore, and they get up and they're just milling about, maybe in a panic or something. They have more thermal energy, they're moving more. They've overcome whatever restriction is keeping them in their individual places. And we're going to see that the restriction that's holding those particles together is the intermolecular forces. Liquids assume the shapes of their containers because those particles are free to move around. They'll just take on whatever shape the container is. Gases are compressible. Liquids and solids are generally not compressible. With a liquid, the particles are already touchingly close. There's not really any empty space there. And so when you put pressure on the piston, you can't squeeze it together anymore. This is a good thing for your brakes in your car because those operate on a hydraulic system where you put pressure on the gas pedal and that puts pressure on the brake fluid. The brake fluid should not compress. It transfers the force from the brake pedal to your brakes. Gases are compressible because there's lots of empty space. This isn't, balloons floating in air. This is particles floating in nothing. Between the particles of air is absolutely nothing. And so when you push down on this, you can squeeze the particles closer together. So if you've got air in your brake lines, then your brake pedal gets kind of soft and mushy. You push on the brakes, and you have to push farther than usual before anything happens because the air in the gas line is compressible. So before you get any braking action, you have to compress the air. Solids, the particles are not able to move relative to each other. How they're arranged falls into two categories, crystalline and amorphous. So a crystalline solid has particles that are arranged in a particular fashion. It's well-ordered, three-dimensional array. There's a pattern. Now, there are lots of different patterns that are possible, but it's got a pattern to it. Amorphous, A is a prefix meaning without, and morph refers to shape. Amorphous solids have no particular shape. There's no order to them, just a bunch of particles just kind of randomly stuck together.
Like rocks?
A little bit. This would be like, maybe you rolled some pebbles or marbles around in glue and just stuck them together. But here, these are going to be packed in together. There's a particular order. So changes in state. We're familiar with changes in state that occur due to changes in temperature because we've all watched ice melt and we've watched water boil, right? So we know that if you take a solid and you add heat to it, you can cause it to melt. You continue to add heat, you can turn it into the gas state, and the reverse happens as you cool it. But we can also induce state transitions by changing the pressure. This works between liquids and gases. If we reduce the pressure on a liquid, we can cause it to vaporize, and if we increase the pressure on a gas, we can cause it to condense. Pressure doesn't have much of an effect on solids and liquids because they are already so close together that the pressure really doesn't do anything.
Isn't pressure somewhat like heat as well? When you put pressure,
Pressure can cause changes in the temperature. Yeah, but pressure and heat are definitely different things. There's a fancy word in there somewhere, but I don't know what it is right now. So here's an illustration of an LP gas tank. So this is what you might have in your backyard for the gas grill. This contains propane. LP gas is liquefied petroleum. It's mostly propane. So it's liquefied at a high pressure to condense it down. Why would we want to transport and store this as a liquid instead of a gas?
Be safer.
It takes up a lot less space, right? We looked at water, and a mole of water was, liquid water is 18 milliliters. A mole of water in the gas state was 30 liters, right? So if we compress this into a liquid, we can store a lot of it in a small container. But it's not going to burn that way, and how do we get it out if it's liquid? Well, it actually comes out all by itself. We've got this valve up here, and when we open the valve, that allows some of the gas that's above the liquid to escape, and that gas is replaced with more particles from the liquid state will evaporate into this space to replace it, and so the gas will come out, and we can burn it and cook our hamburgers.